So this session is about light optics. If you look at the importance of optics, basically it has a huge impact on our daily lives. And we're going to look at how it does impact our daily lives in a various number of ways. So first and foremost, of course, we have vision. Without optics, we would not be able to see anything. Basically what happens, light comes in through this hole that's in our eye, the pupil, and the light waves go through that hole and then hit this red area back here, which is our retina. And because light can go through here and create images back here, we can see. Optics allows us, of course, to also create corrective lenses if the eye, for some reason, is not working properly, and it could be because of a number of reasons. We have corrective lenses that we can use, whether it's contacts or glasses, or even really cool things like 3D glasses. With new advancements in technology, of course, we can also now use surgery to fix problems with our eyes. Instead of contacts or glasses, we can use corrective laser eye surgery. And this is where they actually remove a layer of the eye right here, and then they can go inside and fix what needs to be fixed, whether it's reshaping the lens or removing something from the back of the eyeball on the retina. With advancement in technology as well, we've been able to use microscopes, which uses different microscopes work in different ways. One of the first microscopes, basically, all it was, you place an object on a stage, and then light would focus, shine up through, and that would bounce into a lens, which went up, went over, went up into the eyeball as you look down through the lens. So it's just a series of mirrors that allowed us to make the size look bigger than what it actually was. And then, of course, you have things like the transmission electron microscopes, which are very, very complex, and you have scanning electron microscopes as well. Microscopes have allowed us to magnify things thousands of times closer, and that has allowed us to make even more advancements in the medical field and in lots of other fields that allows us to see blood cells and other types of cells in the body, white blood cells, platelets. It allows us to see things like DNA, and it allows us to look at different other cells, be able to observe things like mitosis, and lots of other stuff. Then, of course, we have telescopes. This allows us to see outer space, and we've made lots of observations and advancements in technology for outer space. And who knows where that will take us in the future. Cameras, very similar to microscopes. The basic idea is you see an image, it comes in through, and you can actually see right here, there's a little lens, and that goes up to another mirror, and then another mirror, and that's how you can actually see when you're looking through one side of the camera, you can see the image on the other side. Binoculars, allowing us to see things far away. And we can even use the light and energy to cook. So what we want to focus on then is the electromagnetic spectrum, and basically this is the wave that has both electric and magnetic parts. Hence the name electromagnetic. And there's different classifications of waves. You have the long waves, which are the slow energy, okay, right down to very short, high energy waves. And this encompasses everything from radio waves, which are very long. And what I mean by long, a wavelength is like this. They can be very long. And then you have things like gamma rays, which are very short and very fast. This is just showing you some of those things. If you look, the radio waves, like I said, a wavelength is basically one trough and one crest. Okay, so if you now look at a wavelength here, it's a much shorter distance than a wavelength there. So it's traveling much faster, much shorter wavelengths. So you would fit more wavelengths in the same distance. So we consider that to have a higher frequency. The only part of the wavelength that we can see, of course, is the visible spectrum, and that's basically this tiny little portion right here. That is the visible spectrum. When it comes to the size of the wavelengths, when you're talking about gamma rays, we're actually talking about wavelengths the size of the atomic nuclei, which is extremely, extremely tiny, of course. Protozoans, these are the pond organisms that we've talked about, and then, of course, as you get larger and larger, that makes more sense. And we use electromagnetic waves a number of different ways. We use them for radio waves, and this is actually how we have our AM and FM radio. This is how we get our TV signals. This is how we use our cell phones, and of course radars. And basically what you have satellites up in the sky, and they send out wavelengths, different spots on the ground. They bounce back and forth all over, depending on where you want to send them. Then we have microwaves. Uses of microwaves, of course, is the microwave oven, the classic microwave oven, but more current things are things like Bluetooth and your wireless modems and your cell phone networks and stuff. We also have infrared waves. These are things like your remote controls and your lasers. You can see here using night vision equipment, okay, that uses infrared waves. And you have your visible light, which is what we can see. This allows us vision. This is the rainbow spectrum, and then any lasers that we can see. Don't get that confused with infrared lasers. We cannot see those, whereas we can see the visible light lasers. Then we have the ultraviolet light, and we've talked about UV radiation and how harmful that can be to your skin. And we don't even realize that that's going on. That allows you to tan and to burn. The UVB light just goes in the epidermis of your skin, that outer layer, but the UVA goes right down to those deeper layers of your skin, and that's where that can cause problems, and you can develop skin cancers and stuff like that. Then, of course, we have the X-rays, and without that, there's lots of things that we would not be able to detect. But X-rays very very dangerous, and you have to be careful. You can only get so many X-rays within a certain amount of time. People who are pregnant are not allowed to get X-rays, and or not that they're not allowed, but they should not, because it can cause damage to a growing fetus. And then you have the gamma rays, and this is rays that we actually use to treat cancer, which may have been caused by X-rays, and that kind of stuff. Now, the type of waves that we can see are the visible light. Isaac Newton, back in the late 1600s, he was the first person to separate white light into the visible spectrum, which allows us to have a better understanding exactly of how we see the different colors that we do, like red, orange, yellow, green, blue, and the other colors of the rainbow. And basically, this visible spectrum is the wavelength that the human eye can detect. That is the visible spectrum. Okay, and you can see just from this diagram, red, the wavelength on red is 700 nanometers, and you go down to violet, which is 400 nanometers. So our visible spectrum is wavelengths from 400 to 700 nanometers. And you can just see what that kind of looks like here, with the red being the longest wavelength and violet being the shorter wavelength. So what I want you to think about from that little video clip is that it's not just cell phone radiation, but we are exposed to wavelengths all the time that we cannot see. And just because you cannot see it doesn't mean that it's not there. So it's something that we have to consider, and this is a true reality of today. And hopefully by the end of this unit, you will learn a little bit more about wavelengths and radiation and all of those possible damaging effects. So I guess the key is there's a lot of good that has come from that comes from optics and electromagnetic spectrums, but there's also a lot of bad things as well. And I guess the whole idea is to learn about both. Have a great night.